And since acids are all about hydrogen ions in water solutions, frequently, that's what we're going to look at. Now, funny thing about water is that in any sample of water, a certain number of water molecules will do what's called self-ionize. They will just split apart. It's a very small number, but that's what happens. So if this water molecule splits apart, you'll remember that every time a hydrogen ion is formed in water solution, it will bond to a water molecule, forming a hydronium ion. So when this ionization of water happens, it splits apart into hydrogen and hydroxide. The hydrogen bonds with the hydronium ion, and the hydroxide ion is there to just kind of float around. So there's a certain number of hydronium ions and hydroxide ions in every water sample, and in pure water, these two concentrations are equal. Okay, so here's a diagram of this equation. Now, if we write the ion product constant for water, like we did in the equilibrium chapter, you remember it's the concentration of the products over the concentration of the reactants. So the equilibrium expression would be K sub W, W for water, equals the concentration of the products over the concentration of the reactants. Now, since water is a pure substance, it doesn't make any sense to ask what the molar concentration is. Okay, so we can get rid of that and simplify it down to this. That K value for water equals the concentration of the hydronium times the concentration of the hydroxide. Now, when you have water at room temperature, the value for this is extremely small. It's 10 to the negative 14th. Okay, so only one in about every 500 million water molecules will self-ionize. An incredibly small number. So then the final expression for the equilibrium, the ion product constant for water, is the hydronium ion concentration times the hydroxide ion concentration equals 1 times 10 to the negative 14th. Okay, now, since these two are equal, we can say that x times x equals 1 times 10 to the negative 14th. So if we solve for those, we say that they're equal. They would both equal 1 times 10 to the I messed up. So this would be x times x. So it wouldn't be 2x, it'd be x squared. So the square root of 10 to the negative 14th is 10 to the negative 7th. So the concentration of hydronium and hydroxide in pure water is 10 to the negative 7th. Now, if you think about the pH scale, the highest number in the pH scale is what? 14. That's where it comes from. And the value for the pH of a neutral solution is 7. That's where that comes from. Now, the job for the next section is to make sense of that. Now, before we get to that, if we make a bar graph of the hydronium and the hydroxide ion concentration in 3 different types of solutions, I'm going to have you pause for a minute and think, what type of solution is this, where the hydronium and the hydroxide ion concentration are equal? Here, the hydroxide ion concentration is much greater than the hydronium concentration. And here, the hydronium concentration is much greater than the hydroxide concentration. So what type of solution is this, this, and this? Now, while you're thinking about that, if you notice, hydronium times hydroxide is a constant. So this times this always equals 10 to the negative 14th. So 10 to the negative 7th times 10 to the negative 7th, 10 to the negative 14th. 10 to the negative 3rd times 10 to the negative 11th, 10 to the negative 14th. 10 to the negative 11th times 10 to the negative 3rd, 10 to the negative 14th. Okay, so what type of solution are these two equal? That's a neutral solution. What if the OH is greater than the H? Oh, that's a basic solution. What if the hydronium concentration is greater than the hydroxide concentration? Well, that's an acidic solution. Okay, so where does the pH scale come from? Well, it's a way of quantifying the amount of hydrogen ion or hydronium concentration in a solution. The P in pH stands for potential, H stands for hydrogen ion. So the pH is defined as the negative log of the hydrogen or hydronium ion concentration. So it's a logarithmic scale used to express the relative acidity or basicity of a substance. Now, what does it mean to be logarithmic? Well, another way of expressing that is exponential. So when you go from a pH of 3 to a pH of 2, that's not just one difference, it's exponentially different. So it's like going from 10 to 100 or from 100 to 1,000. Okay, so a little review of logarithms. We're dealing with log base 10. So the log of 10 to the x, you take the log of 10 to the x, the value of that is x. If you take the log of 10 to the negative x, the value of that is negative x. Now, since we're dealing here with very small numbers, 10 to the negative third, 10 to the negative 11th, we didn't want a negative scale. If we dealt just straightly by taking the log of the hydrogen ion concentrations, then the pH would run from 0 down to negative 14. So we wanted a positive scale from 0 to 14. So we then said a negative of that log of 10 to the negative x would be x. Now if we just switch this equation around, x equals the negative log of 10 to the negative x. So the pH is x. pH equals the negative log of the hydrogen ion concentration. Now, if we plug in actual numbers, if we say the log of 10 to the third would be 3. The log of 10 to the negative third would be negative 3. And this is a reasonable hydrogen ion concentration in an acidic or basic solution. Actually, it'd be an acidic solution. So then if we take the negative log of 10 to the negative third, we get positive 3. Flip that equation around and we say 3 equals the negative log of 10 to the negative 3. Now this would be the pH. Okay, so here we have a hydrogen ion concentration of 2.3 times 10 to the negative second. So get out your calculator and see if you can find the negative log of 2.3 times 10 to the negative 2. And you should get a value of 1.6. Okay. Now, here's the pH scale. It runs from 0 to 14. And actually, technically, it can go down to 0 and even negative. And then it can also go up to 15 and even beyond that. For a really strong acid, the value can be below 0. And for a really strong base, the value can be above 15. So if we look at an acid, now one thing, notice acids run from 0 to 7, and bases run from 7 to 14, where 7 is neutral. And notice the values of the hydronium concentration and the hydroxide concentration are both 10 to the negative 7th. So in a neutral solution, they're equal. Also notice that this times this always equals 10 to the negative 14th. And this plus this always adds up to 14. So if we have an acid, relatively weak acid, where the hydronium concentration is 10 to the negative third, the pH would be, if you take the negative log of this number, you get 3. Now, hydronium times hydroxide always equals 10 to the negative 14th. So if the hydronium concentration is 10 to the negative third, then the hydroxide concentration would be 10 to the negative 11th. If the pH is 3, the pOH is 11. Then if we go to a base, a relatively weak base, the hydronium concentration is really small, 10 to the negative 12th. So if you take the negative log of this number, you get 12. And 10 to the negative 12th times 10 to the negative second always equals 10 to the negative 14. 12 plus 2 equals 14. So one last thing about a logarithmic scale. If we look at a pH of 2 and a pH of 5. First, you have to get around your head around the fact that 2 is a stronger acid than 5. If a neutral solution is 7, then a 6 is a very weak acid. And a 0 is a very strong acid. So how much stronger is a 2 than a 5? Well, how much stronger is a 3 than a 2? Don't say 1. It's 10 to the first. So it's 10 times stronger. How much stronger is a 2 than a 4? 10 times 10. So how much stronger is a 2 than a 5? 10 times 10 times 10, or 1,000.